C dynamic in this project. However, to simplify the project, probably what I would advise you, and in my calculation as well, is I adopt this. Remember, this is earthquake code. This is the wind code. I would adopt this, and therefore the C dynamic at the moment I use this one. Right? Now, for your calculation as well, probably in your report you should provide some explanation why you use C dynamic as one as well, so that the reader will understand why you use one. And for that reason, I think you should put the supplement of the AS 1170 part 2, and then you should be okay. Right? That is the dynamic. Now we apply the wind. Can I what happened? One back now. Remember, the KL factor is 1 now, and therefore it is easier now for you to work it out the wind. You go to the 1, 2, 3, 4, 5, 6, 7, 9. And at each level, you know that there's a wind load in there. To simplify the calculation, I just put the wind load as quite low, and the beam level, right, at each level. Now, you would expect that already the wind load along here is the same, and then the wind there is a little different. It's only half of the area, and that is the length, that is longer, and therefore that wind is higher. Now, you can work it out the NZ value of this, and then you can work at the C fig. Now, what C fig is, the CPX, what it says is for building greater than 25 meters, the CPE is 0.8, but it says that the wind speed will vary across the height of the building. So what it means is, say this is up to 10 meters, up to here, NZ value, we have one factor, correct? NZ value less than 10, you remember that table? I assume that you are very, very familiar with that table now in the code for CPE. And then when you go up to 10, it will be have another NZ and another NZ there. Because of the variation in NZ, you got different speed along the height of the building. All right? Now, you can look at it in your report. However, to simplify the calculation, my sample, I use constant MZ, all right? Using the height from there to there. And therefore, I say the MZ in my calculations is 0.994 for this particular project. That is 28.5 meters high. So that's the MZ. But it's up to you in your calculation. I think when you design as well, you should vary it just for the exercise of the calculation. Don't use it uniform like I did. But remember, if you use it uniform, and therefore your wind load will be less. Remember this. And therefore, if I use 0.8 constantly for 28 meters, my wind load will be higher, and therefore more conservative. And therefore, the building is okay, but it might not be that economical. I'll mention to you later why we use this uniform load when you want to resolve everything. And therefore, you have the wind of 1.2 kPa. That is the wind pressure, right? And from there, I can look at the P value for each level. So the P is just at the C fig as well. Now the C fig, you know that now you're going to 0.8, and the area, the whole building is greater than 100 square meter, and therefore you can use something. The KA factor is 0.8 as well, and plus 0.2, you remember that formula? 0.2 is CPI, that is KA, that is CPE, and therefore, what you have there is 0.84. If you use the, this is the windward. And for the leeward, you got 0.5 times 0.8 minus 0.2 rather, minus 0.2, and that would become 0.2. Now, when for the leeward wind, second or 0.5 multiplied by 0.8 minus 0 as well, that will become 0.4, and that's leeward. And the force on the wind is just simply the pressure multiplied by the sea thick, multiplied by the area. The area is the distance between halfway there and 7 meters. That is 7 meters there. Even 7 meters or differently. Right? So the force is just simply the pressure multiplied by area. So all of those P there would equal 22 kilonewton. And between the bottom there 26, and the up there 11, that is 5, that is 10, and that is 13. Now you got the load, and then you analyze it. Now there's two options for you to analyze it as well. Now obviously next week John will mention to you about the approximate method analysis to get the embedding moment and the shear area. So again, you can use space gas to analyze this. If you use space gas, a very important thing that you must do is you got to input the area, the cross area of the column in, and you got to put the area, the second moment of the beam, the second moment of area of the beam and the column in. Now the reason for that is, you know that if you use 700 by 700 column, and then the I will reduce, and the beam is 600 by 350, the I is relatively much smaller. And therefore, in the frame analysis, you know that if you got the stiffer bending moment, stiffer member, the bending moment will be more with that member, correct? Remember that? Structural mechanics, maybe a long time ago, 2, 3, 4, 5 years ago. But basically the principle is, if you got a stiffer member in the frame, that stiffer member, the bending moment will transfer more into that member. For that reason, you must input the I value, the column and the beam and the area differently into this. Alright? The area is very important as well. If you forgot to input the area, and then when you do the diffraction, it will give you some crazy answer. Right? And you don't even know why. And so make sure that you remember the Oslo, you remember 5,000 more than 5,000 kilonewton, you just squash into that 700 by 700 square column. If the area is small, and just remember that the deformation of the column will be huge, and that's the reason why the area you put in is very important, right? Now, either you can do the analysis using ETEP or space gas. ETEP, I think, Jas is very good in that, so you can ask million questions about ETEP with Jas, right? Or if you want to do the bottom